Okay, so now let's talk about graph traversal. So when we are trying to solve a particular problem using graphs, we'll have to ask certain types of questions. Okay, so for example, is there a path from node A to node B? Or if I have a starting node C, which are the nodes that I can visit from C? Which are the nodes connected to my starting node? Or if I want to get from node D to node E, what's the shortest path? Okay? So if I want to answer these types of questions, then we need to have a way of traversing our graph or crossing from one node to any other node. So here we'll describe two such algorithms for graph traversal. So we have our depth first search or DFS and our breadth first search or BFS. So first off, we have depth first search. So when we use depth first search to traverse a graph, we first select a starting node. So for example, here we have 1. And what do I do in depth first search? So I see what are the nodes adjacent to my starting node. So there is node 2, node 5, and node 6. So let's select node 2 first. So I'll visit an unexplored section, node 2. And from 2, I don't go back to 1 just yet. So let me see what are the other unexplored areas that I have. So there are nodes 3 and 5 that are adjacent to 2 that we haven't visited yet. So punta tayo kay 3. So from 3, there's only one place we can go. So that's 4. From 4, we've already visited 3, so we go to 5. From 5, what are the nodes adjacent to 5? So that's 1, 2, and 4. And we've already been through all of those nodes. So we say that, okay, this is a dead end. Wala na tayong bagong mapupuntahan. So, I backtrack. Okay? We go back to 4. May bago pa ba tayong mapupuntahan? Wala na. So, we go back to 3. Ganun din. To 2. Ganun din. And to 1. And when we go back to 1, doon tayo makakahanap ng unexplored nodes. Okay? So, 6 is still unexplored. So, we go to 6. We mark it as explored. And at that point, we've already traversed or explored our whole graph. Okay? So, what is the sequence of nodes that we visited? So that's 1, 2, 3, 4, 5, and we went back, and 6. Okay? So this is one possible depth first traversal of our graph. So how would we actually implement this in code? So the process of visiting one node to another actually looks recursive in nature, diba? Kasi we start from a given node, then we go to the second node, and we keep exploring, okay? So that kind of exploration is actually recursive in nature. So to do that, we can define a recursive function, DFS. And what are our inputs? We have a graph G and a starting node, V. So first off, we mark the starting node as visited. Then we locate all of the vertices adjacent to V. So if the vertex has not yet been visited, then we call the recursive function. Diba? So we did that earlier. We started at 1, then we went to 2, and from 2, we're actually doing the same thing. We're trying to locate all of the adjacent nodes, and if we haven't visited them yet, then we can select a new node as our new starting node. Okay? So, kailan tayo lalabas sa function call? So, for example, dun sa dead end natin kanina, we went from 2 to 3 to 4 to 5, and at 5, what are the nodes adjacent to 5? So that's 1, 2, and 4. But all of those nodes, if we go through this whole for loop, we see that all of those nodes have been visited. So we no longer have a recursive call. So we stop, lalabas yung function call from DFS G and 5, and we go back to 4. So if I try to map that out, all of our function calls in the call stack, you would have, say, DFS G1, tapos pumunta tayo kay 2, diba? So we have DFS G2, DFS G3, until 5, right? So pailalim ng pailalim tayo in this call stack. And when we get to this function call, natapos tayo without making any new recursive calls. So this function call gets popped from the call stack. And we go back to this function call. And what are the nodes adjacent to 4? So that's 3 and 5. We've already visited 5 and 3. So mawawala rin yung function call to 4 and to 3 and to 2, diba? So from 3, wala tayong pupuntahan. Same with 2. So we simply go back to 1. Okay? And when we get back to 1, at this point, we're now still in this for loop, diba? So what are the vertices adjacent to 1? So that's 2, 5, and 6. But when we go back to that function call, si 2 at si 5, napuntahan na natin. So the only place we can go to at that point is node 6. So I actually have one more function call. So DFS G6. And once I get here, again, there are no more nodes adjacent to 6 that have not yet been visited. So we exit the function call and mapupunta tayo dito, and at that point, there are no more nodes adjacent to 1 that we haven't explored. So this gets released, and we've actually traversed our whole graph once our call stack is empty. Okay? So that's our recursive implementation of DFS. Now, another way that we can do that is actually iteratively. We saw that the call stack is essential to our recursive implementation, diba? But actually, if we don't want to use recursion, we can use a literal stack, okay? So a stack data structure to monitor which nodes we still have to visit, okay? So how do we implement that iteratively without using recursion? So in this function, we declare a stack, okay? We have a stack S, and then we push our first node, V, okay? So we have a stack, right? We have a stack here, and we push our first node. In this case, that's node 1. Okay? Now, we have a while loop here. So while the stack is not empty, then we pop a node in the stack. So that's the node that we want to visit. Okay? So we pop 1. So 1 is now here. Nasa labas na siya ng stack. And we mark 1 as visited. So we would actually have, say, a separate data structure like an array or a vector to represent our visited nodes. So say we have 1, 2, 3, 4, 5, 6 here, and we've already marked 1 as visited. So now, for every vertex that's adjacent to V, which are those vertices? So, di kita dito, pero, so that's 2, right? So 1 is adjacent to 2, 5, and 6. So if we haven't visited those nodes yet, then we push them into the stack. Ibig sabihin, these are the nodes that we may still need to visit. Okay? So we push 2, 5, in the reverse order. So we push 2 first, then we push 5, and then we push 6. Although medyo arbitrary naman to. If we had other labels, say letters yan, maybe B or F or D, then depending on your implementation, that order could be shuffled. Okay? So we push those nodes into the stack, and then um, at that point we're done with that while loop. Okay? So, second iteration, is our stack empty? Not yet. Ibig sabihin, we still have avenues to explore in our graph. So, let's try to pop a node. Okay? So now we pop node 6. So we remove 6. 6 is the 6 is the node we're visiting. So we mark that as visited. Then for every vertex adjacent to that node, if we haven't visited it yet, then we push it into the stack. Pero ano ba yung adjacent kay 6? That's only 1. And we've already visited 1. So we don't do anything. We don't push anything into the stack. And that ends our second iteration. And then the stack still isn't empty. Okay, so we pop a member of the stack again. So 5 is popped, and actually, let's put it here. So we visited 1 first, and then we visited 6, and then we visited 5. Okay, so 5 is the node that we're currently at. And then we do that again. We haven't visited 5 yet, so okay tayo, we mark it as visited. And then let's see all the nodes adjacent to 5. So that's 1, 2, and 4. Which are the nodes that we haven't visited yet? So that's 2 and 4. So these are the nodes that we push into the stack. Okay? So actually we push 2 here again, and we push 4. So after that ends our while loop. Okay? Now we pop 4. Di pa siya natin napupuntahan. So we mark it as visited. And what are adjacent to 4? 5 and 3. We've already visited 5. So we push 3. Okay? 3 gets pushed into the stack. And then that ends the iteration. We pop another element. Okay? We're now in the next iteration of the while loop. We pop 3. Okay? We pop 3. And then we haven't visited 3 yet. We mark it as visited. And then what are the nodes adjacent to 3? So that's 2 and 4. What has not yet been visited? So at this point, only 2. So we push 2 into the stack. And then we've ended that iteration. And then we pop 2. And we haven't gone there yet. So we visit 2. And then is there anything left? So 1, 3, and 5, we visited all of those. So okay na tayo. We don't push anything new into the stack. And actually, once we get to this point, if we pop 2, we've actually already visited that. So okay na tayo. We just pop it, and we go to the next iteration hanggang mawala na ng laman yung stack natin. And at that point, we've already visited all of the nodes in our graph, or that component of our graph. Okay? So naturally, if we have algorithms like this, kung may other components tayo in the graph that aren't connected to our starting node, then we can't visit them. Okay? So in general, our traversal algorithms only apply to a single connected component of our graph. Okay? If we wanted to traverse our whole graph, then we would have to call DFS on other nodes that haven't been explored yet. Okay? So that is how to implement DFS using recursive and iterative implementations. Okay? Using our recursive call stack and a literal stack data structure. Now, just to see na gumagana siya, let's look at a C++ implementation. Okay? So here, I'm using something called Google Colab to run my code. So I have to have the special line, but essentially it's the same. I'm making a file, dfs.cvp, and I will run it in this next segment. Okay? So I have both my recursive implementations here, diba? So in this case, every time that I visit a node, I print it, and then for every node that's adjacent to my starting node, if it hasn't been visited yet, then I call I call the function recursively. And the same thing for the stack, diba? We make a stack, we push a vertex, and while the stack isn't empty, then we pop an element, and if we haven't visited it yet, we visit it, and all of the adjacent nodes that haven't been visited, we push into the stack, and we repeat. Okay? So I call that on this implementation. Okay? So this is an example of an adjacency matrix, diba? So in our graph earlier, we have 6 nodes and several edges. So I implement this as a 6 by 6 adjacency matrix, wherein all of the ones correspond to edges in our graph, diba? And again, our adjacency matrix is symmetric. So if I have an edge from 1 to 2, then I also have an edge from 2 to 1. And I call both the recursive and the iterative implementations. And let's see in what order we visit our nodes. Okay? So I write this onto a file and I run my C++ file. I compile it and I run an executable. So as we saw earlier, if I use the recursive implementation, we traverse it in that order, 1, 2, 3, 4, 5, tapos 6. And then if we use the stack, then dahil si 6 at si 5 ang nasa ibabaw nito in the stack, they get popped first. So I visit 6 first, then I visit 5, and I go in that order. Okay? So this actually forms a type of tree. Okay? So if I try to see the edges that I traversed, so I started at 1. And then I went to 2, to 3, to 4, to 5, tapos bumalik ako, and to 6. Okay? So this actually forms what we call a spanning tree, or a tree that spans or connects all of the components, all of the nodes in the component. Okay? So that's one possible spanning tree, diba? Using our recursive DFS order. The other way that we did that was we visited 6 first, and then we went to 5, then to 4, then to 3, then to 2. Okay? So this forms another spanning tree. Okay? So it's a tree with the minimum number of edges needed to connect all of the nodes in a single connected component. Okay? So there. So those are 2 possible implementations of our depth first search on graphs. So in the next section, I'll be discussing a second type of algorithm, which is breadth first search.